This big casserole dish, this big container. All this food. Thanks, guys. But I can't. Set the week.
There's no way.
I take that class, I'll take your word for it.
You know?
So.
Kind of more relaxed.
I think they put NBCS.
I'm not sure.
There's
27 of those, basically just plotting, alkalinity against. So there's a course of the moment. So. A lot of this.
I'm gonna try it. We'll see.
So, find the site, a lot of the site, right?
Yeah. Maybe just everyone
They're all
else.
very
It's not.
fun.
Maybe everyone else.
That's. Yeah, I didn't want to screw with those. It's just SI against the.
Yeah. Let's take pictures and fix them later.
We could have switched it. Yeah.
I do. Yes, that's how it is. Oh, is it all right? This is on my calendar. Thank you. Here's my warmest. Sweet. Yes.
So. Have you done it? Just kind of great. I haven't even received an invoice. So it's just looked at it. I don't know what these are. It's 32 hours.
I'm getting the one. Yeah. Yeah.
So it's like. Well,
Yeah.
let's get started. Some of you, I noticed are here today, but not on Friday. I took the exams back on Friday. If you didn't get them, and I've got them, and I can give them to you. What I want to do today is continue on with the topic that we've been working on, where we're going to use wells to help understand the properties of aquifers. So what I want to do is show you how to tell you about these tests and show you how to analyze them. And then we're going to go and meet in the field. Mentioned last time that we would do that on Friday, but we're actually, we had that class where we went and went to that lecture that kind of pushed us back by class. So we're going to meet instead of Friday, we're going to meet on Monday. Okay. It's in the Clemson Bottoms, which is, Perimeter Road. Where like the sports facilities are. Yeah, so it's down there. Next time, don't worry, we still got a couple of classes. I'll bring a map and show you how to get there. You can walk there from here. We're pretty darn close here. It's just kind of down the hill, in back of us. So from here, you could probably walk there in 10 minutes. You can also drive there. So the idea is that we'll just have this class period worth of time down there. And I'll show you about the plumbing test, and I'll show you about the assignment. There's a homework assignment that involves the well tests down there at the bottom. So I'll show you about that. Okay, so here's the stuff we're gonna work on today: transient well testing. So the performance of a well as it changes with time. We'll look at how to do some models of this, the mathematical models, and then how to use the models to calculate aquifer properties, primarily transmissivity and storativity. Okay, so a transient well test. What's going on here is that we're going to apply some kind of a hydraulic stress to the well, and we're going to measure the response of the aquifer to that stress. And from that response, we're going to estimate the properties, hydraulic conductivity, transmissivity, sortivity. Okay, so that's going to be the approach. Apply a stress, see how the aquifer responds to that stress, analyze that response. So by stress, I mean that we're gonna do something to the well, basically to the volume of water in the well and or the pressure. Those are going to be related. So we're going to change that and see how the well responds. So there are three main ways that we can do this, that we can apply a stress. One is that we can, a constant rate test, we can pump water out of the well at a constant rate. So in this case, the flow rate coming out of the well is constant. And we measure the drawdown at the well and at piezometers. So we pump water out of the well, that's constant. There's not really anything happening there. It's just the same always. But then the pressure of the drawdown at the well and piezometers, this is changing with time. And this is then the signal that we're going to be interested in. Okay. So let me just draw a little sketch so we can kind of visualize this. So here's the well, and we pump water out at a constant rate. That causes the drawdown to increase, the water level to drop, and this propagates out here, and we're going to measure also the drawdown out of the well, or out of the monitor. Okay, and let's say that this then it's going to do that at the time. Okay, that's one way of stressing the well. Another way, though, is if we have the well here, we can go and drop the water level in the well a certain amount and hold it there. Okay, and then we still have to have a pump in the well. But if we do this, so we drop the water level in a well by a foot, say, then we're going to pump water out, and the rate at which water gets pumped out is going to change with time. So let me do this. For a constant rate test, let me draw a Q, the function of time, that's like that. And then delta P as a function of time. This is drawdown, and that's going to look like that. So for the constant drawdown test, I have a similar pair of plots. In this case, the drawdown is constant, and the flow rate is going to change with time. So what happens is if you have a well and you drop the water level here initially and hold it here, you can kind of visualize like this. So if the drawdown comes to here, let me get a darker color here. So if the drawdown comes to here initially, then the head in the well is going to look like that right after we drop the water level. So see how the gradient is really steep right there? So the flow will be really fast at first, and then with time, the head is going to go like that. The gradient right here at the well flattens out. So the flow rate coming out of the well decreases with time. So for the constant drawdown test, flow rate looked like that. Okay, so those are related, but different. This is typically the kind of test that you do in a conductive or a productive aquifer. If you have a permeable aquifer and you can do a pumping rate like this and have enough drawdown to measure, but not so much that you draw it down to the well, the pump, then this is what you would do. This kind of a test, this is often what's done in a well that is, or in an aquifer that has low hydraulic conductivity. Low hydraulic conductivity aquifer is not going to be able to really, I mean, you would pump the well dry if you pumped it at a constant rate. So you have to modulate the rate and it has to drop with time in order to hold the head pump. So this is for, say, high permeability aquifers and lower permeability. Okay, then another way to do this is to stress the well by changing the drawdown suddenly. Okay, so if we have this, and then we, typically what we'll do is raise the water level up to here. Let's say if we just pour this much water in the well instantly, okay, then what will happen is the water will flow out into the formation and the head will drop. So we'll change this suddenly and then we'll measure this during recovery. So it doesn't really involve a pump. We just have a mechanism to change the water level. In some cases we could add water, but what we'll see is that another way to do this is to just take a cylinder or take a body, a slug is where the name comes from. Take this thing, it's heavier than water, and we drop it in the well, and that displaces the water, displaces this much volume. And then that water flows out into the well, and we measure the response. Okay, so those are the three different types of stresses that we can apply and responses that we would measure and analyze. All right, so here's the constant rate test. This is just really the conceptual model of what's going to happen. So we start pumping, we drop the water level in the well, and we get a drawdown cone that looks like this. We keep pumping, and we're pumping at a constant rate, right? So the gradient right here next to the well, it stays constant because that is the flux, and the flux into the well is staying constant. So the drawdown now looks like this. The radius of influence increases. So as the radius of influence increases, the rate at which the drawdown has to occur to release water from storage, that rate is going to get less. So we can get the drawdown is going to get slower. So we keep going and keep pumping, and here this is meant to show where we go and we have less of a drawdown here in a unit of time because the radius is expanding. Okay, so that's what the drawdown looks like, the function of time, or that's what the head looks like as a function of time. It's dropping here, and the drawdown looks like that. So this is, the slope is steep at first, and then it flattens out because this area is increasing. Okay, so now we're done with pumping. We stop pumping. and the aquifer recovers. Okay, so this is the recovery part of the test. And when we stop pumping, if we look at this and we stop pumping, we've got this gradient right here. So this means water is flowing into the well. If we stop pumping, that gradient is still there. We're gonna have water flowing into the well. So stop pumping and that happens. Water is flowing into the well, and from this time to this time, that much water, enough water to fill up the well bore, that by that much has flowed into the well. The gradient has flattened, and the water level has risen here. But look at what's happening out here. The water level here is falling, and it continues to fall for a bit after we stop pumping. And then it goes and continues to recover, comes up. We're having water flowing into the well. So even though we're not pumping, there's still flow in the aquifer. So we're still having flow dynamics, and the properties of the aquifer are still important. Water level is rising, and then we keep going, and eventually the water level comes all the way back, but we have to supply this water from somewhere that we've recovered. So what it ends up looking like is that you have a recovery that looks kind of like a mirror image of the pumping. It recovers quickly at first, and then it slows. And if it's really a confined aquifer that's isolated, it won't recover completely. But in many cases, with the wells that we have, they do recover. They recover back all the way. Okay, so we've got two stages: pumping and recovery, and we can get information from both of them. All right, so the rate at which the water level drops is going to depend on the hydraulic connectivity. That's going to dictate like what this gradient is, right? Because the gradient here is going to be whatever the flow rate is. We're going to need a certain flux into the screen here, and that flux is going to be determined. Well, the gradient is going to be determined by the hydraulic activity. As we pump water out, we're removing water from storage here, well, here down in the aquifer, and we're removing it as a result of dropping the pressure. And keep in mind that there's an aquifer here, and that's where all the action is. We're moving water from storage here. So the storativity is going to matter. And then the aquifer thickness will also be important. The pumping rate, we need to know that, to presumably know that. And R, that's the radial distance away where we're making measurements. So this is the head in the well, drawdown in the well, but we would have a plot that looks similar if we were measuring the hydraulic head out here in the monitoring well. Okay, so this curve depends on these things. These are aquifer properties. This is a property of the aquifer too, the thickness. And then these are properties of the test, how much we pump, the pumping rate, and where we make the measurement. Okay, so here's the plot of that data. I just sketched it on the previous slide, but here, this is what it would look like if you were to get some data. And you notice that this is a linear scale on both axes. If we make this a log scale, then the plot looks like that. Okay, so it's kind of flat here, and then it starts to curve up, and it becomes straight here on this semi-log plot. And then it drops quickly here if we plot just as a function of log of time. Okay, so that's what these data here look like. So we saw this before, on last class, we saw that we were doing some pumping here and here's the monitoring well. And this was the drawdown at the monitoring well. So it goes up like that. And we then have this point where, I don't know, on my screen, this looks a bit elongate here, but at this point, it still should be circular. And then this part is straight. And then as we go and continue to pump, this interacts with this stream over here, this is lattice down. Okay, so that's that graphic that we saw last time was the response that you would expect if you pump a well at a constant rate. Okay. So that's what's going on. What the strategy is going to be is to come up with an analysis for the drawdown as a function of time that depends on those aquifer properties. We have that, we can take that function and fit it to the data and see what aquifer properties we need to match the data. So we analyze the drawdown to determine these two main properties of the aquifer. And then there's another thing that we want to measure, the well efficiency. There are the drilling process can cause clogging of the pores around the well that affect the well efficiency. And then there's another quantity that we want to get, the steady state specific capacity. Remember we said 2 classes ago that the specific capacity was the ratio of the flow rate to the drawdown at steady state. So these are the things that we'll be after. We want to come up with ways to estimate those. Okay. So what we need is a way to predict what the drawdown is. The strategy is going to be that we do a pumping test, we measure the drawdown as a function of time. And then if we have an analysis that predicts the drawdown as a function of time, then we can take that and fit it to the data and adjust the aquifer properties so we can match the data. So we need to do a simulation. We need an equation for the head or for the drawdown in the aquifer. So what we're going to assume is that we have a constant pumping rate in a confined aquifer. And at first, we're going to assume the aquifer is fairly ideal. So it's homogeneous, isotropic, and it's an infinite lateral extent. So if this is the aquifer here, then the boundaries top and bottom are impermeable. We're only getting water out of storage from this layer, and this layer goes on forever. Okay, so no matter how long we pump, we're still able to remove water from storage in the aquifer. It's transient, and there's no recharge. So these are all the specs that we saw a month or so ago when we were looking at the governing equation for hydraulic head in an aquifer. So if we apply all of these constraints, then this is the governing equation. The Laplacian of the heads is equal to the rate of change of the head and their storativity and transmissivity. So yeah, from day 10. Then go back and look it up. Remember I gave you a handout, had a page of all these different versions of the governing equation. So for these cases, this is it. Okay, so to solve it, we need boundary conditions. So the boundary condition is that at the radial distance equal to the radius of the well, the flux is equal to the pumping rate of the well divided by the surface area of the well. Okay, so that's the boundary condition right here. And then the boundary condition at R of infinity is equal to the head is equal to, that's the initial head. Okay, so this is a boundary value problem in applied math, and it can be solved analytically using methods that we're not going to get into right now. Okay, and as it turns out this problem also governs the conduction of heat in solids, and that is a problem that has widespread engineering applications. So this problem, this equation with boundary conditions like this has been solved back in the early part of the 1900s, had been solved for many different cases for heat conduction. So this guy recognized that, and it turns out he went down the hall to his friend, and who was an engineer who studied heat conduction, and he said, here's the problem I have. And the guy said, oh yeah, okay, this is a well-known problem, here's the solution. And the solution is that the drawdown is equal to that. Okay, so there's pumping rate, the hydraulic conductivity and thickness. That thing there, that's what's called the exponential integral. Okay, so this is, I don't know, that might look a little intimidating, how do you deal with that? But it's the exponential integral, this thing, it's just a transcendental function like log or cosine. In your calculator, you have these buttons where you have a number, and you press a button and it gives you another number. So that's basically what's happening here. You put a number in here, and that number goes here, solve that integral, and you get a result. Okay, so Tice found that the drawdown we could express like this as the exponential integral of that thing. U has these parameters in it, RS, the properties, and there's time. Okay, so this thing here is the drawdown as a function of time, which is what we want. And the properties here, K, there's S, there's B. So the aqua properties are in here. This thing we can plot as drawdown as a function of time, and then adjust K and S to fit the data that we have. Okay. So this is the mathematics. We can write the integral here as with a symbol there. So the natural log, everybody's familiar with the natural log, that's defined in terms of an integral. And so it's similar to this, just like a button on your calculator. So here we can write it like that, where we just have exponential integral represented like that. All right, so that's the Tice solution. The Tice solution is one of the, I would say, more famous. It's like the Tice solution and Darcy's law, one of the more famous equations in hydrogeology. The guy that Tice got this from, his colleagues told him, Tice went to the guy and said, hey, I'm going to write this paper. You want me to put your name on it? And he said, nah, everybody knows that. Everybody knows that solution. It's just trivial. You can just use it. So he missed out. So anyway, the Tice solution, this is widely used. And when you see it in the book and in the Fetter book, you don't see it called the exponential integral, or at least not widely. What you see in hydrogeology is that this is equal to what's called the well function. It's really just the exponential integral, but the well function, I think, makes it a little more accessible. So the well function is the function of u, there's time. So you can take 1 over this and it ends up being there's time. And then this stuff here has units of 1 over time. So this grouping has no dimension. The dimensions of it cancel. So this is what's called a dimensionless time. And the well function is, the argument here is 1 over the dimensionless time. So we can write it like that. This thing is tabulated, so you can just look it up in tables. You don't have a homework assignment where you do that. There's got some tables of this back. Okay, so that's all good. You'll work with the well function in the homework assignments. What I want to do is what I want to use in class is a simplification of this. And what we're going to do is say that this exponential integral, if you this function is well known with mathematicians, and they've studied it in detail. And what they found is that the exponential integral, you can approximate this, the exponential integral. I don't know, can you read this? Is it readable? So what it says is that E1 of u is equal to minus gamma minus natural log of u plus u plus u squared of u times 2. Okay, that's this thing. So this is a constant called Euler's number, and there's some other terms. So u is this stuff with time in the denominator. So as time gets bigger, u gets smaller. So if you have a series like this, as u gets smaller, if you take a small number and square it, it gets even smaller. And then there's another term here that's got u cubed in it. So you take a small number and cube it, it gets really small. You square it, it gets smaller. And here's the small number itself. And then a log of u, the log of the small number, is going to be bigger than the small number itself. Okay, so as you get smaller, that ends up essentially being 0, or we can ignore it. And then as it gets smaller yet, then we can get rid of that one, and smaller yet, that one. So if we let time go on long enough, u gets small enough, we can ignore all of this stuff and just use that. Okay, so this is nice because what it means is that this exponential integral, we can approximate it as minus gamma minus u. This is just natural log of u. So the exponential integral, after we let time go on for a while, can be approximated as a natural log. Okay, so that's going to make analyzing this a lot easier. All right, so then what you do is you say, okay, this gamma, here's gamma, 0.5772, blah, 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 blah. So if you take the natural log of 1.78, then that's pretty close to that. So you replace this with log of 1.78. And then if you take minus that, then it equals the log of 1.78 times u, right? That's the rule for adding and subtracting logs. And then u, we can substitute in this stuff. So the natural log of u, go through here, it's gonna be approximate log, natural log of, there's time, transmissivity, R squared S, the constant. Okay? So that makes life a lot simpler than dealing with the exponential integral. Okay. So this is the pi solution, and we've got this from the previous slide. Right, so let me write it out. All right, so this is Q over 4 pi t. I'm going to calculate 1 over 4 pi, and it's this. Okay, and 4 over 1.78. Oh, actually, never mind. Hold on. Got ahead of myself. So remember that the natural log of x is 2.3026 times the base 10 log of x. What I want to do is set us up so we can use base 10 graphically. Okay, so I'm going to take this and substitute it in here. And that makes this 2.3 U. Okay, now I'm going to group this stuff together and have it's a little simpler way to write it. Okay. All righty. So if I have log of this stuff, I can write this like this. I can write this log as okay. This plus that is equal to that. You know, you just go and multiply together these arguments when you add logs. All right. So this, if I plot the data as a function of log of time using semi-log plot, then this behaves on a semi-log plot, that just behaves like X. And this is the slope. And this is the intercept. It would be that thing times that. Okay, so on semi this thing is got the equation of a line. So that is the slope semi-log graph. Okay, so what it means is we can plot the data up and measure the slope on semi-log and then solve for t. So slope is equal to that, and that equals that, and we can then solve for t. So that gives us a way to estimate what the transitivity is. Okay. So remember now, we saw this when we plotted this up, delta p on the function of log of t, it looked like that. I saw that it was a semi-log straight line. That slope ends up being the slope that we talked about. What we also can do is project this back here to drawdown of 0. Okay, and we'll call that time t sub 0. So we can say that the drawdown equals 0 at t equals t0 sub 0. So the drawdown can equal 0 when the log, well, the log of 1, 0, right? So this will equal 0 when that equals 1. So we get delta p equals 0 when okay, so when this stuff, I'm using 225 from those numbers. So when that equals 1, this equals 0, drawdown equals 0. Right. So this is t sub 0. So there's s. We can multiply through by s. Get that. Okay, so we know t from the previous page. You measure t sub 0 off the graph. We know what r squared is. So we can calculate s. So the procedure is going to be, we measure the slope, calculate t. We measure t sub 0, calculate s. That's how we're going to, that allows us to analyze the data just using, plotting it up on semi-log and doing it graphically. So this function here, this is a simplification of the Tice solution. It was determined by a guy named Jacob. So this is called the Jacob solution. And this says the drawdown is a function of time. and also of distance. So we can use this to plot the drawdown as a function of time. Like that. There's the log function of time. And this is, when we plot it like this, it's called a type curve. We can also use this to plot the drawdown as a function of distance, where we would hold time constant. So here's drawdown for the head as a function of distance. Also a logarithmic function. So remember last time when we saw a plot of the drawdown cone? This is if we took this and revolved it around, that would be the drawdown cone. So we can use the Jacob analysis for both of those. All right. So what I want to do is to analyze, to go back to this. And in order to do this, we need to calculate the flow of this semi-log plot. So this is a handout. And I want you to take a moment to calculate the slope. Guess while you're at it, also calculate E0. Units, these two. Check it out. You know. That way. So, yeah, try doing it. Use two forms and these. The slope would be the same, right? Try doing it. So. So. First, come on. Your noise, sir. Okay, so I haven't seen the right result yet. Okay. So look, here's the deal. So people, everybody that I've seen so far, and I don't know, maybe I misinterpreted, but they're saying there, change of y there and change of x, this is like 200 minus 20, right? So that would be 1 over 180 is the slope right there, right? 1 over 180. So the slope here, it's the same, right? Well, it should be. But this is 2,000 divided by I don't know, 200. Right? So this would be 1 over 1,800. Okay? So here's the deal. When you do the slope on semi-log, it means something different than when it's on Cartesian. This means the slope is the change in y per log cycle. Not, so forget about these numbers. That's one. That's 1 log cycle, that's 2 log cycles. Okay, so the slope is 1 unit divided by, that's 1 log cycle. Right? Because that distance there is 1 log cycle. So there's that distance. So that's the slope of 1. Because the slope is delta y per log cycle. So the units are units of feet. This has no units. Okay. So we can see that if we go back here. So this is Q, right? This is length cubed per time. This is length squared per time. This has to have units of length. No time in it. And the reason for that is because of this, because the slope on semi-log is done on a per log cycle. If this is not semi-log, then we can do it the way everybody was doing it. Then if it's not semi-log, it looks like this, and the slope is changing. Okay. So key thing, when you do this analysis, when it's semi-log, treat this as one, well, treat the slope as change of y per log cycle. Then we'll be on.
So we've got like 4 different slopes then?
No, no, this is change of y of 1 per log cycle of 1. This is also change of y of 1 per log cycle of 1. And same here. So if you do it per log cycle, it works out. The slopes are all the same all the way.
Is the slope just 1 in that case?
The slope is 1, yeah. 1 foot. It's 1 foot. You can have to keep these units. Cool. Yeah.
Okay. Oh, to see you.
Yeah. I can do a lump start on the, yeah, I can just start. Yeah, Did you? The whole life. I say cyber attack or whatever. That's probably, it's like 4 minutes.